We are very glad in posting this webinar on the foundations of software-defined vehicle. And most of you might be aware that 4 major innovations happening in the automotive industry are the electrification, automation, shared mobility, and connected mobility. I hope you know in depth about what is happening in the 4 dimensions. So we just wanted to move from the normal fuel based system to the battery based system under electrification, and we wanted to enhance the battery performance. So the research works are going on the first domain. Similarly, a lot of people wanted to have so many automations in their vehicles, and we would like to enjoy connected mobility also, and the shared mobility is also taking a big place in the industry. So now, where does this software defined vehicle fit in? Okay, so this is the next thing that I'm just bringing to your focus. So here, the automation and the connected mobility, they give to the hybrid rise of the software defined vehicle. Okay, so the software defined vehicle, I'll just give you a simple definition to understand. There are so many definitions from the view of many stakeholders. So I can rightly say that a software defined vehicle in an automotive industry can be defined as software is given the prime importance to drive the functionality, take control, and give user experience rather than the hardware. Because nowadays, in the traditional architecture that we are currently moving with, it gives importance to the hardware. Okay, once the start of production is initiated, we don't have anything to change over that. Okay, that is the thing happening. And when some bugs are found, they do vehicle recalls and go for some feature enhancements or upgradations. Okay, that is the thing happening as of now. But in this term, the software defined vehicle, we are going to make software as the prime importance, that is going to drive the functionality of the vehicle. So this means a physical experience that we are getting from the vehicle. And the second thing is, it is going to take over the control. The software will take the direct control of the vehicles, and it is also going to enhance the user experience. So this is how I'm just putting the simple definition for the software defined vehicle. And what does this give us? So that would be the next question. So the software defined vehicle will allow for greater flexibility, okay, in the existing architecture, and it will result in scalability. So when I take a term about the term scalability, so we can have over the air updates, so that we can have feature enhancement, feature upgradation in a very easy means. And this will also enhance the real time connectivity. Okay, and it will give way for continuous innovation and adaptation to the emerging technologies with the existing vehicle what the user is having. So these are the privileges that we might be enjoying when the software defined vehicle comes through on the road. And as I already mentioned, the position that it is taking in the 4 major innovation domains is the hybrid place of automation and connected mobility. So automation means it includes ADAS and autonomous driving as well. And why this switchover is happening at a larger scale now? So this may be the second question that is arising in our mind, because vehicle, it is an important thing that has to be given enough consideration, because it takes care of the safety and security means of a person inside as well as the persons outside on the road. So prime importance is given to security and safety, both for the persons inside as well as the persons and the properties outside the vehicle. So when this is there, why is it we are switching completely towards another thing, that is the software defined vehicles? The two reasons that I just surveyed and inferred was, one is the increasing customer dissatisfaction. Okay, because nowadays the persons they invest a very nominal amount for their smartphones, but they are able to enjoy so many feature upgradations meanwhile with the same hardware that they are holding. Okay, whereas they spend a lot, in Indian terms lakhs and lakhs for a car, But when they wanted to do some feature enhancement or upgradation, they have to go for the next model, so they have to resell or go for exchange, where they have to go for reinvestment as well. So this customer dissatisfaction is the prime reason. And the second thing is the shifting industry focus. So apart from the normal OEMs and the big market players in the automotive field, the new players like Tesla, Lucid Motors, VinFast are rising fast with their autonomous vehicles, level 5 autonomous vehicles on road. And this is further increasing the curiosity of the customers. Okay, so as a result, they wanted to have a concept called smartphone on wheels. Okay, which means the car, the infotainment system, and what else you are having should have larger interactive screens. They must have seamless internet connectivity. They must have regular over the air updates, so that you can install the application that you want and enjoy and make your journey much more enriching. Okay, so this is the expectation of the customers. And this is going towards a consumer centric design. Okay, what I mean by consumer centric means, rather than focusing on the nominal vehicle features, now the OEMs and the other vendors, they started focusing on the customer's experience. Okay, and the customer's experience, it is an extension of a digital lifestyle that we are enjoying with the help of smartphones now. Okay, so as a result, all this thing drives and gives the stimuli for the software defined vehicle to emerge up in the market. But as I mentioned, all this thing, whether it is directly applicable to the existing architecture, whether it can come true, whether it can keep up the same safety levels. So this is our next question when we speak about this. So we have to just consider the current traditional architecture and what are all the uh, major things that are preventing us from moving apart. Okay, so just imagine the subsystems in our current day car. They have their hardwares and softwares provided by different vendors. Okay, now a single source is not giving the support. So we get the different systems, like from brakes to powertrain, the body parts like infotainment, etc., from different vendors, and they're all integrated with a unique software architecture. Okay, so in this way, and also we have so many product variants for a single we can single product. Okay, so we are also most concerned about the functional safety, and we do quantify the risk level of each of the subsystems, and we categorize it either as ASIL A, B, C, or D. Okay, and we can also exclude it by bringing under the term quality management. Okay, so these are all the things that we primarily consider for the current day vehicles, that is the traditional vehicles which are on road now. But simply speaking, in order to enhance the customer experience and to give them satisfaction, we cannot skip out any of these valid points. Okay, so we have to consider keeping all these things static. We have to concretely maintain all these things, and along with this, we have to consider giving the user experience as well. Okay, then how is it possible? Okay, so the major OEMs, like they are all suggesting the term habitat on wheels rather than smart wheels on wheels, which means we have to enhance the customer experience, okay, by retaining all the functionalities of the current day system. Okay, so this is the main primary goal of the software defined vehicle. So we have to enhance the customer experience by keeping hold of all the physical vehicle experience and the functional safety standards that we are currently having. Okay, so this is the primary goal. So we can rather call it as habitat on wheels rather than smartphones on wheels. So in order to achieve this, what are all the things that we must focus upon? Okay, so what is the architectural revision that we have to bring in? Okay, for that, what are all the major hardware supports and the software supports we need? So this is the next thing that we have to think for a while. Okay, so we wanted to focus upon the architectural changes that we wanted to impose, and to get that architecture implemented in real time, we wanted to go for the next set of hardwares, the high performance computers, rather than the normal conventional ECUs that we are using. And we also have to consider the integration of AI into it, artificial intelligence into it. Then only we can get autonomous status in the vehicles, that is self-driving nature can be brought in real time onto the road only with the help of AI integration into the existing architecture. Okay, because they have to consider the sensor inputs, they have to perceive the environment and make real time decision, that too in the real timing gaps. So all these things can happen with the AI integration. And to implement it in a short while, what must be the software design or the pattern that we are going to apply? So we are just going to focus on these three perspectives in the following slides. So am I clear in setting up the objective of what is SDV, why we are moving for SDV, and what are the three major things that we wanted to focus to learn the foundations for SDV?
Yes.
Fine. Okay. So here we have the two different architectures. Okay, so this is the traditional distributed e-bar architecture that the vehicles are currently following, and I have also proposed the domain centralized e-bar architecture with the HPCs. HPCs are nothing but the high performance computers. Okay, we'll come to this later, but just I wanted to make you understand the architectural difference clearly between a normal traditional vehicle and a software defined vehicle. Okay, so here in the conventional traditional vehicles, based on their functionality, we are grouping the ECUs. I hope all of you are aware of this. So the ECUs in charge of doing the uh, power generation, transmission, distribution, and all those things, they come under the powertrain. And the ECUs that takes care of providing comfortness and the other assistance to the drivers and the co-passengers, they come under the body electronics. And we do have chassis and safety domain. It takes care of the vehicles interaction, that is the driver inputs carried over to the wheels and the interaction of wheels with the road. So all those functionality comes under this chassis and safety. And we do have the infotainment domain. Here we are majorly taking care of all the media related things and the communication. Okay, and also denoting the status of all other domains to the driver through this. And here we do have a central gateway that is used to make the communication in a very fast real time manner between the different domains. Okay, and we have the tester here to do the diagnostics as well. So this is how we generally experienced our distributed e-bar architecture in our traditional vehicles. But how can I make this architecture to do the two different functionalities? So what are the two different functionalities I'm meaning about? One is to retain the same safety levels and the physical experience of the vehicle of current day. That is the first thing. And the second thing is, to that I have to enhance the user experience by giving additional features, okay, on continuous integration and deployment basis. Okay, so how can I make both the things to happen at the same time? So what changes I have to do in this existing distributed architecture? So that has to be the next question in our mind. So to answer this, see, we have categorized this domains earlier. So to those individual domains, we are allocating a high performance computers. Okay, so the HPCs are mostly preferred in SDV development. Okay, why? Because is they have superior computational powers. They can handle larger number of sensor data. Okay, they can do a complex processing in real time. Okay, and they can also integrate the AI capabilities in them while doing the processing. and they will provide seamless integration of software driven functionality. So this is what we were expecting. We must have scalability and flexibility. Okay, so in order to enhance this flexibility and scalability, we wanted to have the over the air updates as well. So this HPC will be efficiently managing the over the air update services also through the service oriented protocols that we'll be discussing in future. Okay, so hence we consider HPC as the main component in the SDV architecture. So now to each domain we put this HPC and we connect all these HPCs to the gateway. I'm sorry. Okay, so excuse me. Hello sir. Sir, சார் வெபினார் போயிட்டு இருக்குங்க சார், எஸ்டிவி வெபினார். ஓகே சார். Okay. So I just told you that HPCs, when you include the HPC into the domains,
Kavita, you went on mute.
okay, am I audible?
Yes.
Okay. Okay, fine. So when we introduce a HPC into the existing domains, the HPCs will take care of the complex data processing work. Okay, because we wanted to do autonomous driving. In autonomous driving and including of ADAS features involves handling lot of sensor data and sensor fusion algorithms to be implemented, and perception of the environment requires AI, artificial intelligence, to be integrated. So all those complex processings can be done efficiently and in real time by the high performance computers. Okay, and they will also have the ability to go for seamless integration of new features. Okay, and also to enhance the existing features in a better way by providing efficient over the air updates. Okay, that is why we put the high performance computers into each domain. Okay, as a result of which we get this particular architecture. I hope now you're getting some idea onto this. So I have to now bring in two different things. Okay, one is the normal vehicle features has to be retained. To that I have to bring the smartphone features also. Okay, but bringing the smartphone features onto the vehicle, it is bit complicated because smartphones, they have a defined standardization in their software architecture, but we don't have such thing in the existing vehicles. So what all the changes I have to do at the architectural level, that is what we are concentrating upon. So I just explained you that to the existing 𝐅𝐴 architecture we are including the HPCs. HPCs are nothing but the high performance computers. Okay, and see, this is the zonal architecture that we are going to slowly migrate towards. So all the sensors, actuators, and the lower level microcontrollers or the ECUs will be grouped and brought under four different zonal controllers: front zonal, back zonal, left and right. And all these zonal controllers will talk with each other and also with the high performance computers, and we'll have high performance computers allocated for different applicational functionalities, like for basic vehicle computation and networking, and for infotainment, for ADAS, etc. Okay, so this is how we are going to migrate the existing architecture into a zonal architecture with high performance computers integrated into them. And now the central computing device, okay, a high performance computer will be considered as a major element that will have connectivity to the cloud to get the OTA services later on, so that what we were aiming at, integrating the enhancing the existing features, or also to bring new features onto your vehicle without any exchange, can happen through this architecture, through this modified architecture. So now what would be the result when we modify the existing traditional 𝐅𝐵ARI architecture with a high performance based zonal architecture? Okay, what would be the differences that you can feel? Okay, so here in the earlier domain architecture, ECUs will be doing 85% of your processing work, and HPCs, we are not majorly focusing upon that HPC. Okay, whereas in the zonal architecture, see, when you deploy the HPC into the same domain based segregation, your HPC's work will be less prioritized. Okay, whereas in the zonal based architecture, the HPC will take up 85% of the processing. Okay, and only 15% will be remaining taken care by the ECUs under the front zonal controllers or back zonal or left or right controllers, meaning HPCs will be very efficient to do the calculation in real time compared to ECUs, because they will be having hardware accelerators in them. Okay, so hardware accelerators or a special hardware circuitry, okay, that will bypass the software looping and will give us more efficient outputs in terms of communication services like CAN communication or LIN, FlexRay, etc. Or it will use packet forward engines, PFE, to enable faster Ethernet communications through hardware accelerators, or the AI data processing can be enhanced using the corresponding hardware accelerators. We do have even other hardware accelerators, special form of hardware devices to enhance the security, like hardware security engines, so that the cyber security and all other threats can be serviced with the help of those features. So this is the uh, primary advantage that we'll be getting out of this zonal architecture. And the very important point that I would represent is ECE consolidation. Since we are consolidating the ECUs, we can reduce the number of ECUs involved in the zonal architecture. This is how we are cutting down the hardware cost also in the zonal architecture, because a single HPC can replace n number of ECUs. So in that way, you are doing ECU consolidation and bringing down the hardware count in the existing architecture. This is one primary advantage. And the next thing is high upgradability. With the help of HPCs, you can directly get connected to the cloud, and they will have hardware accelerators to take care of the safety as well and security aspects as well. So you can have easy upgradation of the features and functionalities of your vehicle. So this is how we are shifting from an 𝐅𝐵ARI architecture to the zonal architecture. And still we haven't revealed the secret how to remove the clash between the two worlds, or how to bridge the gap between the two worlds, because SDV's main focus is to retain the current physical experience of the vehicle. Along with that, it has to add the digital experience. Digital experience means equivalent to the smartphone experience we are enjoying. So if you look at the physical experience of the vehicle, we are making use of functional safety standards, ASIL categorization, real-time processing, okay, and all those things. And we do apply V model as the software development lifecycle methodology to this. Okay, whereas if you look at the development perspective of digital experiences and the corresponding services, we have to strictly go with the agile methodology, okay, which is totally apart from that V model. So here comes the here comes the clash between the two different objectives, and there is a big gap between the two things also, and how we are going to sort it out. Okay, when we get some idea on bridging this gap, then we'll be very good to go with the and proceed with the SDV implementation also. And now I'll give a just introduction about the HPCs. Okay, I was talking at so many places about HPC. So HPC is nothing but the high performance computer. Okay, again, it is a hardware system. Okay, so as I already mentioned, it will have multiple hardware accelerators. You may have hardware accelerators for CAN, flex-ray, LIN communication, which can be called as LLCE, and you may have hardware accelerators for networking, for Ethernet, which you will call it as PFE, packet forward engine, and you may have hardware accelerators for security, as hardware security engines. And similarly, you can have HPCs that have special hardware circuitry for image processing also. Where is my cursor? Yeah, image processing also have hardware accelerators. So when you have hardware accelerators for image processing, you can use that particular HPC for ADAS applications. Okay, so when a hardware accelerator is present in a HPC with LLCE functionality, PFE functionality, and security functionality, you can prefer that as a gateway element. Okay, and similarly, you can have hardware accelerator for artificial intelligence and integration also. So those type of HPCs can be used for giving autonomous driving features. Okay, so based on these functionalities only, we are going to choose which HPC will be chosen for this particular purpose or for your particular project. Okay, so we do have so many examples for the HPCs. HPCs can have either processor architectures or cores in them, or they can have both controller and processors in them. Okay, so we will have so many examples. I will limit myself to the NXP, NVIDIA, Qualcomm, and Jacinto. Okay, so let us see here. See, we have NXP. This particular HPC, it will act as a gateway element. Okay, because it has hardware accelerators for CAN communication, for LIN, flex-ray, and for networking it has got a special hardware accelerator, and for security aspects also it has got a hardware accelerator. So that is why we just prefer NXP for gateway applications, and for edge processing also it can be used, because it is going to do processing at a greater speed. So it can enhance your security features, it can do networking services, and do vehicle control also. So when you want these types of services, you can choose NXP as your HPC choice. And Infineon, it is going to act as a good cockpit controller. So cockpit, it is a term that we are borrowing from the aviation, because there the pilot will be having the single control, central control for all the other body modules. Similarly, here in the future SDVs, the driver can take the central control for all other functionalities. So for this, connectivity is very, very important, and for connectivity to be enhanced in real time, we do want certain hardware accelerators, and those hardware accelerators are present in the Infineon HPCs. So we can prefer Infineon for cockpit controllers. And the third choice is the Texas Jacinto, and this Jacinto can be a good choice for ADAS feature development and for infotainment purpose as well. Okay, and Qualcomm, again it is a system on chip. We have so many variants from this Qualcomm. This Qualcomm also can aid Infineon or replace Infineon for cockpit services and connectivity services. It can give you a single infotainment system with larger screen space and with good DSP support, etc. And the NVIDIA Orin and NVIDIA Drive, so these are very good for handling AI data, AI processing, and doing autonomous driving, because they have hardware accelerators to do artificial intelligence and other algorithms to be implemented at a much faster way, and hence they can be a preferred choice for autonomous driving. So this is an overview about the various high performance computers that you can prefer for your choice of the project. And these are the few screenshots of those HPCs that I was explaining you. So this is the NXP S32G274A. So ANSYT is currently at a greater level. We have explored about these particular HPC, and we have done so many POCs on this. and it has a CAN accelerator, Ethernet hardware accelerator, and the main thing is it has 3 M7 cores and 4 A53 cores in it. Okay, and multi-core communication can be done inside this HPC through interprocessor communication framework. Okay, and it has also ASIL-D certified. Okay, so you can deploy it for the automotive grade projects. And the very interesting thing is it uh, sticks with a service oriented architecture, so some IP services can be implemented on top of this, and testing infrastructure is also provided by this particular gold box, and we can do hypervisor on this. So with the help of hypervisor on the same target, you can implement multiple functionalities, a safety and a non-safety function, isolated and working on the same hardware. This way only you're going to reduce the number of ECUs. That is why you're bringing down the cost. And it is also AutoSAR compliant. You can use POSIX OS also, and you have cyber security modules also, hardware modules to enhance the security reasons. So that is why we particularly prefer this microcontroller of our choice, and this acts as a gateway controller. Okay, and as I already mentioned, we have Qualcomm. This will be the best choice for the cockpit connections, which will be the single central control element for all the other user experiences. In this, I can mention about different user experiences like infotainment, climate control. Okay, and you can also mean uh, what else? Wherever in the body part you do have different controls segregator, right? So they can all be brought under a single control with the help of this Qualcomm. And we also did an infotainment project on this, developing a display on this Qualcomm SoC. And the third thing is the NVIDIA drive, which can be a preferred choice for the ADAS functionality implementation. Okay, and now how the various technologies are giving its impact on the software defined vehicle. Okay, so artificial intelligence, it is playing a major impact on SDV because it is contributing to 62 percentage. Okay, so as I already mentioned, when we wanted to go for autonomous driving, the perception of the environment around the vehicle is very important. Okay, and capturing the sensor data. Okay, making real time decisions. Okay, and doing all other decision making, it relies with artificial intelligence. And also user experiences can be enhanced with artificial intelligence. So I can quote you so many examples, like for example, you are driving a long way to a picnic. Okay, so you are taking your child with you, and if the child is feeling drowsy, the artificial intelligence technique used inside those HPCs, with the help of sensors, can sense the uh, child's bad health or ill health, and they can make adjustments automatically, like dropping down the windows, or adjusting the air conditioner levels, or bringing some ambient lighting into it, or asking you to change the driving pattern by giving some warning. So this is one example I'm giving. Similarly, I can give you so many examples, like when you go for electrification, we wanted to consider the battery life and the charging hours, because during the peak charging hours you will be charged high, whereas if you optimize the charging hour, you can save your economy. Okay, so there again artificial intelligence will help you in fixing a schedule in prior, or in, fixing an appointment to the service stations, and balancing your battery level based on that. And similarly, when you return out of your gym work, okay, you have to get into your car with an ambient lighting, and other user experiences, like you have to hear a good music that you really enjoy or you like, or your air conditioner should be set to the desired temperature you want. So when you enter the car out of your gym, the wearable that you were wearing, the smart watches or something that you are wearing on hand, will signal your vehicle. Okay, and the vehicle will set all these things for you, the lighting, the climate condition, the music, and everything for you, so that you can get into the car and get relaxed over there. So these are the few examples that I'm telling you how artificial intelligence can be used to enhance the user experience. Similarly, high performance computer takes up 53% of the SDV architecture, because as I said earlier, to do AI integration, to integrate so many sensors and to do complex processing works and to do over the air updates, HPCs are very very essential, and they take up the 53 percentage. And the all other things like electrification, okay, maintaining the battery level, when you're taking your pets out for a shopping, you cannot take them inside the few places, so you have to keep them inside the car. At the same level, you have to maintain the battery level. Okay, so likewise, those user experiences and those applications, you can consider under this as an example. And cloud computing and data analytics, it occupies 31 percentage. Cyber security, it's very very important, because when we speak about software defined vehicle, the vehicle's sensor level data and actuator level data have to be dealt by the other vendors also. So it has to be secure. That is very very important. Otherwise, a viral attack will collapse the entire system. So we have to give great concern for the cyber security. And some newcomers to the market, they are also exploring on integrating augmented reality and IoT into the emerging technologies. And vehicle to everything communication, again it is a major technology. And sensor technologies, we do have smart sensors coming along with IoTs to directly send some data to the cloud. So all these things play a major impact on the software defined vehicle. And this is one such example, the Nvidia that is used. Okay, it uses AI technology inside to do so many works, like you can fix your navigation path in an optimized way based on the traffic data, real time traffic data. And AI based risk prediction can be done. Insurance risk analysis can be done. So this is a good feature for the OEMs. Okay, when they claim the insurance, what you have to do, and it will give a good connected vehicle communication also. Okay, so AI can be used with the help of NVIDIA HPC to do all these real-time functionalities, and that is how it is going to enhance the user experience, keeping alive all the functional safety features of the basic vehicle that we are currently having. So until this, I hope I'm clear, or do you have any queries on this? Is it okay to follow?
Hello,
Yeah,
I
it's
just
okay.
have
If you have
two
some major
questions.
queries, I'll just schedule it after the software design part. Or if it is very essential and critic with this topics, you can just ask me.
Ma'am, those all the things in Rolls Royce cars available, no?
I'm sorry, your voice is not clear.
No, in all those things, it is in available in Rolls Royce cars, no?
You are asking me that all those features are available in Rolls Royce car, right?
Yes.
The features that I was listing out.
Mm.
Okay, so see, our objective is the software defined vehicle concept has to be brought in road in all the countries to the uh, middle economy people as well. Okay, we cannot simply focus on the high budget cars alone. So how it can be implemented in an affordable way? I hope that should be the objective. Have I answered your question?
Yeah, okay.
Okay, fine. Anything else? Shall I proceed?
Uh, Hello, am I audible?
Yeah. I hope if there are any queries, I can take it later. But if it is very technical, you please ask me now. You're able to follow me, right?
Yes, yeah. I just have two
Yeah.
clarifications alone
Yes,
with
yes.
respect to. I mean, you showed some architecture with respect to NXP, I guess. Can you go to that slide if you don't mind? NXP architecture.
This one.
Yes, yeah. So this alone I just have it out. Maybe you can note this down and can explain this a bit clear.
You want me to explain this architecture?
Yes, yeah. Again, I mean, it was a bit confusing this part of
Okay.
it.
Okay. See, actually, I told you HPCs have both processors and controllers on them. It is an SoC, right? It may have multiple cores on it. So the cores may be either processors or controllers or a combination of that. Okay, so that is what I was telling you. This particular NXP, it has A53. A53 is a microprocessor, so it has 4 A53 cores on it, and it has 3 M7 microcontrollers on it.
Okay.
Okay, and they A53 and M7, they can make use of the hardware accelerators present on that particular SoC. So hardware accelerators are special circuitries, hardware circuitry that will be aiding to bypass the software and directly fasten up that particular work. So LLC will help in faster CAN communication. PFE, this is a particular hardware to make Ethernet communication and networking in a much efficient way. And the hardware security engine, it is hardware that will be aiding in enhancing the security in a reliable way. Is that clear?
Yes, that's clear. Yeah.
Okay. And top of it,
So,
you have to think so many
Just one
layers.
minute.
I'll come to it
just
later.
Okay.
interruption on here. So hardware accelerator and special circuitry, is it mean that any boosting of RAM or what is a special circuitry? Can you give one example? Hardware
Yeah.
accelerator. How
You
it
just
accelerates?
consider the LLC. Okay, it is a hardware that can take care of CAN communication. So this particular hardware will do the routing, so that the software routing part will be left free. It can be bypassed. So in this way, if you use the LLCE for CAN communication, I have a proof at the end. I'll show you. You can transmit a CAN message in 20 to 25 microseconds when you use a hardware accelerator. Whereas if you use the normal existing software based CAN implementation, if you go for that, it will take approximately 5 to 10 milliseconds for the transmission of a message. So this is an example I can give you.
But
This we
CAN
have.
normally will not transmit in microseconds. It's in milliseconds only, right?
Yeah, it is in
CAN
milliseconds only. That is what I told you. When you go for hardware accelerators, this can be achieved.
But how the synchronization is happening then in the CAN communication, arbitration and all those things will collapse, right? So it will not communicate.
Yeah, the hardware
Clearly,
accelerators, they just take care of the routing, right? And to go in depth with this, I hope we must, if you're interested, you can just approach us in person.
No, it is not clear what you are explaining in the special circuitry and hardware accelerator.
Okay.
That's my
See,
concern. But if
normally,
you are able to answer to that, you can separate the session because a lot of people are here. You can
okay.
separately
Yeah, I
answer
will
in
give you the
this one. But it's
justification
not
now.
clear.
See, in a normal CAN communication, the CAN controllers or CAN transceivers, what you're using, we will be just using the interrupt or polling method. Am I right?
That is for interruption. Yeah, go ahead, please.
Yeah, just to check whether you have got a CAN message, or after sending a CAN message to indicate, you will be using such things, right? Whereas
No. Mm-hmm.
here, when you go for an LLCE, that is a low latency communication engine. Okay, this is a special hardware circuitry that will manage the runtime routing.
I got it. The routing you were telling, how it is acceleration is happening. So that is my concern. How acceleration means, how it's you are telling that high performance computers. Agreed.
Kavita, I think
But
so. We are actually paused and just we don't have a time, 4 o'clock, and then maybe
Yeah.
the objective will not be covered. Please maybe take it up in the next afternoon.
Okay. So
Almost
for this
remaining
part,
200
I'll
people
just
are
try to
waiting.
post
Yeah.
later in the group. Okay.
yeah, it's not clear, but you can mention whatever you want to explain. You can explain
Okay.
the group.
See, we have that option in the HPC. So my objective now is to just transfer this to you, and how that is exactly working, we will just see it in a separate session or sometime later. And now the thing is to make you clear about the software design part. So I was telling you that there is a wide gap between the two things. In achieving the vehicle experience, we want V model to be retained. In getting the digital experience, that is the user experience, we want the agile methodology to be followed. But how to bridge this gap? Okay, so for this, we wanted to get learnings from the existing smartphone industry and from the internet. Okay, because they are doing lot of DevOps, development operational, and they do lot of continuous integration and development as well. Okay, so from those two industries we learn a lot, and we try to do this particular thing, decoupling of hardware and software. So decoupling of hardware and software, so this is the big challenge that we are having in front, and when we are able to achieve this, we can remove the clash between these two worlds. Okay, so this is the thing that we are proposing for the software defined architecture and how it can be done. Okay, so for that we have lot of vehicle operating system definitions. Okay, but most of the definitions will have these three things as a common objective. One is a vehicle operating, see, so many OEMs are working to get a modern vehicle operating system that can cater the needs of the customer. So here the specialized software runtimes for different functionalities, it is a primary objective, key component, and hardware and software decoupling, it is required, that is another secondary component, and over the air software updates must be done. So a vehicle operating system that you choose must be able to satisfy these 3 points. Okay, so how it can be achieved? So there are so many open source communities that are helping for the software defined development. Okay, the first one is the Eclipse SDV. They do give so many open source projects which we can take and work upon. And we do have 𝐸𝐸𝐴, the Connected Vehicles System Alliance. So this is also an open standard. So this is very, very important. I will just tell you how this 𝐸𝐸𝐴 standard is helping us to fix the gap between the two levels, and how it is helping us to decouple the hardware association with the software. Okay, in the following slide. And the third thing, SOFI. So this is a particular community, they are just helping us in virtualization. Okay, so this 𝐸𝐸𝐴, they are just trying to tell us how to bridge the gap in the architecture by giving a tree like API structure. And SOFI, they are giving so many open standards with respect to the virtualization techniques. So they are working in association with ARM to give an virtual ECU. So before coming for direct testing and implementation, we can do everything in the virtual ECU. Testing can be done in the virtual ECU, so that we can minimize the cost of investment, and we can maximize the time to market also. And I was telling you, I'll show you about 𝐸𝐸𝐴. See, look at this particular example. When we segregate the architecture into a zonal architecture, so imagine we will have one such tree-like architecture in the body like this. So in the vehicle, you have body, cabin, chassis, etc. So here, you just consider this vehicle, cabin, seat. Okay, see, vehicle, cabin, seat, row 1, position 1, headrest, angle. So this is how they are going to establish the relationship between the low level sensors and actuators and the higher level APIs. So this is one example API that I have shown you here. So when we start breaking this and give a decoupling to the hardware and the software, we can make the APIs to talk to the lower level sensors and actuators. So in this way, we are bringing standardization in the software architecture. And this is how we are going to abstract the software from the hardware. Okay, so this is one such example, and this standard has been proposed by 𝐸𝐸𝐴 VSS, Vehicle Signal Specification Association. Okay, they tell us how to relate the APIs with the lower level particular sensor in a tree-like architecture. Okay, and see, this is how we are going to bridge the gap. This is the zonal architecture that we are going to modify. High performance computer will be sitting on the vehicle on board. This high performance vehicle will help in doing this abstraction. This will make the software to talk with the direct hardware. Okay, and the decoupling is done with the help of this high performance computers, because at the top level, the application softwares, okay, they will be broken into functionalities, and each functionality can be coded as microservices. Okay, and several microservices will be combined to give you a single application. Okay, and each microservice has to talk with each other through APIs, interfaces. Okay, and the relationship between the APIs and the sensors will be established by these standards and the architecture. With the help of these references, the high performance computer will bridge this gap. So how this is bridging? Here is the defined architecture. Okay, see, you have your offboard services here, cloud services here. Okay, virtualization will happen offboard here, and this is your onboard. Here you have two different types of services. One is quality based services, which does not sit up with functional safety, and another one is onboard functional safety related services. So you are classifying your microservices like this, which will come under quality, which will come under functional safety likewise, and you are making it to sit at that particular layer. And at the bottom you have the zonal architecture. So you have three layers here. The top layer speaks about the offboard component, cloud, and the middle layer speaks about the onboard services with different functionalities. And here the microservices and the APIs are distributed. Microservices are the basic functionality units, and APIs will be the communication medium between the microservices. And at the bottom, the lower level layer is your exact hardware. Okay, see, your sensors and actuators are connected to your zonal controllers, and internally they have CAN and other communications happening. Okay, so here there are two levels of APIs. From the cloud to the onboard, you have vehicle to cloud APIs, and from the onboard to the lower level components, you have signal to service APIs. So all these things come true only with the help of this high performance computer will be sitting at this level to unreveal this API and give the necessary signal informations to the zonal controller, so the zonal controllers can take that action. So here the COVESA standard is being used and it's being applied here. So this is how we formulate the service oriented architecture for the SDV, so that it can maintain the functional safety also, and it can enhance the user experience also with the cloud connectivity. Is this clear?
Hello, Kavita. I have a question. I'm a beginner, so questions may be a little stupid. But if you just go back to that original, the previous diagram. So in this diagram, okay, so you mentioned zonal controller, which is a high-end ECU. But how is it? Which one is here the high-performance computing, which is a part of the COVESA?
We haven't directly shown you any high performance computers here.
Okay, all right.
That is why I'm relating you with this. Your APIs, okay, will be communicating with your vehicle through the HPCs. Here we are just formulating the layer.
So may I assume that ZC is a kind of an HPC in this diagram, just for understanding?
Which one you mean?
The ZC. The ZC boxes.
Zonal controller. No. Zonal controllers, they have to talk with the HPC. So you may consider HPCs will occupy. See, I'm coming to the HPCs now. Don't worry.
Okay, thanks.
See, can you just relate this? See, the same layer diagram I'm taking with the other dimensional perspectives. So you can see the HPCs, where it is seated. I told you, no, they will transform the APIs into signals for the zonal controllers.
Understood that. Thank you.
Yeah, from the offboard, you have the onboard. In the onboard, the first point of communication will be HPCs. The HPCs will be connected with the corresponding zonal controllers. So you have to just correlate with this with the earlier zonal architecture diagram that I showed you some slides before. Is this clear? And here you can see what are all the hardwares at each layer. Okay, and what are all the operating systems preferred at each layer? What must be the offboard?
Give one example where the adaptive AutoSAR use case will come into picture in this.
The adaptive AutoSAR use case, see here you can use it for functional safety based application. You can
Thank you.
see this adaptive autos are used on onboard functional safety applications. See, in the previous slide, I mentioned this yellow color layer. It is onboard functional safety related microservices will be occupied in this layer, and those microservices coming into this yellow layer can work with the adaptive AutoSAR middleware. You can relate it with any of the use case that you know. Is that clear?
Yeah, clear.
Even that zonal computer will have that adaptive AutoSAR, right? Classic
Yeah,
and
you
adaptive.
can have it for the controllers also.
Yes, yeah.
When you have it for the HPC, you can have so many functionalities loaded on a single HPC. But when you put it on top of a zonal controller, it is meant for one particular functionality alone. So just make this difference alone clear.
Oh, okay, yeah, understood.
Okay, because on the HPC, we can deploy a hypervisor. Over the hypervisor, you can have so many functionalities on a single target, single board. In that way, only you are going to reduce the number of ECUs.
Okay, Kavita,
Yes.
Balaji. So I have a question. So the entire architecture, even including the HPC, whatever is shown, does it depend on AutoSAR architecture, or it can be collaborated with the non-AutoSAR environment?
Not so. It is the entire architecture. It is not dependent on AutoSAR. That is why I'm clearly depicting the C. This learning more than a year we are working on SDV. Okay, and in a single hour, it is very, very difficult for me to explain every concept to a beginner or to someone working at the intermediate level.
Yeah.
Okay, I
Got
hope
it.
you can understand the difficulty. I'm not saying it is not possible for me to make you clearly understand, but the thing is, only AutoSAR it is not needed, because when you go for enhancing the user experiences, most of the thing has to depend upon Android OS and the other things, right?
Yeah.
So in that case, you need not go for adaptive AutoSAR or classic AutoSAR, or even an real-time OS is not needed there. But for your vehicle functionalities, you must depend upon RTAS, adaptive AutoSAR, or classic AutoSAR, or whatsoever it may be.
Hello.
Yes.
What are those runtime
Kavita,
containers
we
on the
have
top
the
of
last
hypervisor?
5 minutes, Kavita. You try to conclude.
Yes. Can you just give me some time to finish it so that I can answer all your questions?
Yeah.
Yeah, containers. See, containers. I told you we have microservices. We have lot of functionalities in a vehicle. You imagine more than 100 functionalities. So each functionality will have n number of microservices. Okay, and if you wanted to keep your microservices isolated, protected, and containerized, you can go for containers. And container runtime will be used to execute that on your board. See, when you go for over-the-air updates, you in the mobile phone, you just imagine when you download an app, it gets executed instantly and you just enjoy the application, right? Similarly here, the containers concept, it needs a brief elaboration. So as of now, I can say you that container will have all its dependencies and libraries in it. So when you just download a new feature or some file, it will be automatically executed and brought into your usability.
Okay, got it. You can go ahead.
Yeah. So see, just I'll give an overview. This is how your base layer platform has so many functionalities to take care: security, safety, networking, diagnostics, okay, processing with the A53. If it is a microprocessor, how should be the processing done? How should be the scheduling done? If it is a microcontroller, it depends upon the firmware and the testing and integration. Okay, at the top level, you have the application, and here you have the middlewares. Okay, so if you just look at this, we have two different HPCs here. This is NXP in green color, Infineon in red color. You can see if you make proper decoupling, meaning if you abstract the software from the hardware, whatever may be your platform, only the platform changes, the application and interface remains same for all the for irrespective of the hardware. I hope you get this point now. Why I meant for decoupling or abstraction between software and hardware. So when you make perfect abstraction, only you need to change the base platform and the application interfaces remains the same for all the platforms. Is this inference clear?
Yeah. So here the 𝐭𝐢𝐨𝐬 is providing the API standardization.
Yeah, COVESA has so many branches in it: VSS, VCC,
No,
VCA,
no. I am
etc.
talking in terms of this image. When you say,
Yeah, yeah.
when you
So the
say
relationship
hardware,
between APIs and hardwares will be given by some open standards like COVESA.
yeah. So then only you can standardize, right? Because
Yeah,
if
yeah.
you're starting below hardware, something has to be standardized.
Yes, of course.
Even in the conventional autos are actually that only the base platform which is going to be changed, right? Like see the MCAL, if you change, that's going to be enough. The application and then the intermediate layer, what you call, or middle layer RT, it is going to be same, right?
Yeah, yeah, of course. But we are not restricting or constraining ourselves with the AutoSAR and a single microcontroller or an ECU level. Now we are looking at a broader perspective in a top-down approach from the cloud, off-board service to on-board service, and then to zonal controllers, then the lower level ECUs, sensors, and actuators. So
That's
if
the
you
basic difference.
yeah,
Yes. Yeah.
so just when you see it from the top-down manner, you will get a clear understanding of what I'm delivering now. Okay, now this is what we are trying to do from the simple V cycle that we are following. I cannot state it as simple V cycle. The traditional V cycle, we are going towards the development and operational. So we are planning, doing the code, building, testing, releasing it from the cloud. The users will deploy it, they will operate and give their feedbacks. You are monitoring their feedbacks, and you again go for redoing on it. Okay, so this is what is the software development life cycle change that we are expecting. And I'll just narrate, take 2 minutes of you to explain the works that ANSET has done so far. We were initially focusing on the S32G2 hardware, that is the HPC from NXP. We have done so many POCs on it. We have customized so many Octo projects for the board. We did the multi-core communication through IPCF between A53 processor and an M7 core. Okay, and we have implemented suspend to RAM for power saving feature, and CAN communication was done through LLCE through the hardware accelerator. We have done the containerization through Docker. Okay, and we have implemented some IP application on the Zen hypervisor on the NXP board. And we have also done a simple OT over the air update with the local server so far, and we are now about to do it with Amazon Web Services and so on. And adaptive AutoSAR also has been implemented on the HPC of our choice. Okay, and this is the particular HPC, and this was our use case. And I hope we are running out of time, so I'll just stop it here for your queries.
The slide will be shared after the session, right?
Sir, I hope Bhishma sir will be answering you this.
It will be available in the YouTube itself. We are live telecasting this, and you can see that itself.
Any other technical queries to be answered?
Can I ask a question? You've mentioned on a number of occasions the cost-saving possibilities, but what's the typical cost of an HPC versus an ECU?
I'm sorry, I couldn't properly get your question.
What is the typical cost of an HPC against an ECU? Because if you tell me it's 10 times more expensive, then
it is expensive than an ECU. The NXP board that we are using is about 3.5 lakhs in Indian rupees, and of course the thing is you can replace so many ECUs with a single HPC, and you can give enhanced features lifelong for the vehicle.
That's the reason for my question. How many ECUs do we need to get rid of to cover the cost of an HPC?
Okay, that actually varies from one project to the other, right?
Yeah, obviously, yes. But typically,
so I cannot give you a predefined value for you, integer value on this.
Sorry, you must be able to, because typically the cost of ECUs is fairly standard nowadays. but the
Okay.
cost of HPCs is unknown at the moment.
Okay. So I'll try to work on this and give you a numerical value, an approximate value, considering a particular use case.
Okay. A second question, and it was a point that you made about the sensing the occupant comforts,
Okay.
and the car actually being able to change the HVAC or even open the windows. Do you realize how distracting that is if suddenly the car starts deciding to open the windows?
Okay, you mean that if we give the user experience likewise, it will be a distraction, right?
It's a huge distraction.
Okay, that is why we meant about the cockpit controllers, which will be having a central control. It will be giving you and generating you certain warnings, and it will be asking for the driver acceptance to do that. So you in SDV, the main thing is for each release of the application, they can get the user feedback and then go and revise it accordingly. And if they find that the released feature or functionality, if it is not preferred by so many customers, then they will likely remove it. So in future, the OEMs are planning to generate revenue through the new features that they are going to bring under continuous deployment. Okay, so through user feedback only we will be validating it and then releasing it. So of course it will not be a problem and a major distraction.
Sorry, we're way past it being a problem. The first 10 minutes of getting into any new car is spent by the driver disabling all the warning systems that are currently being fitted.
I'm sorry, can you please repeat?
I said it's too late to be looking at this problem. The first 10 minutes of getting into a car nowadays involves disabling all of the multitude of helpful systems that have been put onto the car by the driver, because the driver finds them all distracting or time consuming.
Okay, see, like the features that you preferably keep in your smartphone, only the owner of the car decides whether he has to use that feature or disable it. If you likely feel that as a distraction, you need not go for using that application in your car. You need not install it. So that is the privilege and preference we are giving. Users and the owners can choose which application they want, and they can pay for that and get it. Otherwise, they can simply discard it, right? So this is the important advantage that SDV will be offering you. You have to pay initially for the commodity functions, and later on for the features released. If you are interested, you can buy and install it. Otherwise, you can simply discard it. I hope I have answered your question, right?
I think you are incredibly naive about automotive usage and ownership.
Hold on. Please, I hope this is not being seen as I think this is an issue you might have to take with OEMs. This is a session on software-defined vehicles and people who are interested in learning about this. Sorry for interjecting.
Yeah,
but I understand what you mean.
Yes.
So this is not something that she can answer. She is not a spokesperson for all OEMs. Do you understand?
I hope your answer is valid, and he might agree with that.
Okay.
I don't really care. Thank you.
Yeah, thank you so much.
Thank you, Kavita.
Yeah, thank you so much.